Right now, 35,000 feet above your head, two massive commercial jets are screaming toward the exact same coordinates at like 500 miles an hour.
Yeah, and the only thing stopping them from colliding isn't the pilot's eyesight.
Exactly. It's a single, completely invisible string of mathematical vectors doing calculations millions of times a second.
It really is wild to think about.
It is. And we're talking about the notes from Day 30 Skew lines, theory, domains, code, specifically Chapter 11, Sections 11.4 and 11.5.
Right.
And the mission for this deep dive is to understand how a totally abstract concept, lines that share the exact same universe but never physically touch, literally keeps airplanes from falling out of the sky.
And stops your smartphone from catching fire, actually.
Yeah, and makes the shadows in your video games look photorealistic. I know you love pulling back the curtain to see how things actually work, so today we are custom tailoring this journey to unpack exactly how one equation rules everything from the microscopic to the orbital.
It is a phenomenal topic because, well, we usually treat theoretical math and physical engineering as completely separate disciplines.
Right, they feel totally disconnected.
Exactly.
Right.
But this equation is the literal boundary condition for reality. So we are going to strip away the intimidating Greek letters and the textbook formatting and look strictly at the physical mechanics behind the math.
Okay, let's unpack this, because before we can talk about planes or circuitry, what actually is a skew line?
Well, it helps to start simple.
Right, so picture yourself drawing two lines on a perfectly flat piece of paper. You're working in two-dimensional space.
Yeah, standard 2D geometry.
And those lines really only have two possible fates, right? They either cross each other at some point, forming an X, or they are perfectly parallel, running side by side forever like train tracks.
But you have to step off that flat page and into three-dimensional space.
Okay.
If you hold two pencils in the air, you can angle them wildly away from each other,
Yeah.
so they aren't parallel.
Right, they're pointing in totally different directions.
Right, exactly. But you hold them at totally different heights, so they never intersect.
Oh, I see.
Because they exist on entirely different non-parallel planes, they will never touch, no matter how far you extend them. And those are skew lines.
So how does a computer actually track those pencils? The source material mentions R vectors and lambda multipliers, which honestly sounds like a remarkably quick way to lose the plot.
I completely agree. The textbook definitions, like line 1 being R1 equals a 1 plus lambda B1.
Yeah, that just sounds like alphabet soup.
It does. So instead of looking at it as an equation, look at it as a set of instructions.
Okay, instructions for what?
To pin down a line in 3D space, you really only need two distinct pieces of information.
Just two.
Just two. First, an anchor point. Where does the line start? We call that the A vector.
Got it, the starting point.
Right. Second, a compass direction.
Right.
Like where is it pointing? That is the B vector.
Okay, so anchor and direction.
Yep. If you have an anchor and a direction, you have defined your line.
But what about those lambda or mum variables in the notes?
Those are just scalar dials. You turn the dial up to stretch the line out to infinity or turn it down to shrink it.
But wait, if they stretch to infinity, how do you measure the distance between them? I mean, they are constantly moving further away or closer together, depending on where you look along the line.
Well, we aren't looking for just any distance. The mathematical goal in the text is to find the absolute shortest orthogonal distance.
Shortest orthogonal distance. Okay, let's break that down.
Imagine holding those two pencils again.
All right, I'm holding them.
Now, imagine slipping a toothpick between them and sliding it around until you find the exact spot where that toothpick forms a perfect 90-degree right angle with both pencils simultaneously.
So it's perfectly perpendicular to both lines at the exact same time.
Exactly. That perpendicular sweet spot is your shortest orthogonal distance.
Wow, okay.
And mathematically, finding that toothpick requires two tools. First, to find the angle between the lines, that theta, the math uses a dot product.
A dot product.
Right. It looks exclusively at the compass direction, those B vectors, and essentially calculates how strongly they are pointing with or against each other.
Which isolates the directional relationship, right? But it ignores where they actually live in 3D space.
Precisely.
It doesn't tell us how far apart they actually are.
No, it doesn't. So for the distance, we use a different tool, the cross product.
The cross product.
Yeah. When you take the cross product of your two direction vectors, the math does something incredible. It produces a brand new third vector that points perfectly perpendicular to both of your original lines.
So it automatically generates the exact orientation of the toothpick.
Yes. It essentially builds the scaffolding.
That is so clever.
It is. Once you have that new perpendicular vector, You take a line connecting your two anchor points, and you mathematically project it onto that scaffolding.
Project it. What do you mean by that?
Think of vector projection like shining a flashlight from above and measuring the length of the shadow it casts.
Okay, I can picture that.
The length of that shadow falling perfectly along your perpendicular normal vector, that is the absolute shortest distance between your two skew lines.
So we have a mental model now. We have a mathematical toothpick acting as an invisible measuring tape, driven by cross products and projections.
Exactly.
But let's get out of the theoretical space. So what does this all mean?
Let's apply it.
Yeah, let's go back to those airplanes. How does finding a perpendicular vector keep you safe at 35,000 feet?
Well, in aerospace engineering, specifically air traffic control, those planes are physical skew lines.
Okay, they're the pencils.
Right. They have an anchor point, which is their current GPS coordinate in the sky.
And a direction vector.
Exactly. The direction vector is their heading, altitude, and speed.
But wait, a plane isn't a static line stretching to infinity. It's a physical object moving through the air.
Yes, very fast.
At 500 miles an hour, isn't there a massive margin for error? I mean, a shift in wind changes a plane's vector instantly.
That is exactly why the calculation isn't a one-and-done math problem. It's a dynamic, continuous engine.
It's constantly running.
Always. The system calculates what's called the CPA, or the closest point of approach.
Closest point of approach, okay.
The computer assumes both planes will maintain their current vectors, and it projects those flight paths forward in time.
Ah, so it's looking into the future.
Right. It is frantically hunting for the single moment where that invisible toothpick between the two paths is at its absolute shortest.
So if you're on flight A and another plane is flight B, it doesn't matter if you look out the window and think you're going to hit.
No, not at all.
The computer knows exactly how many miles apart you will be when your paths finally cross.
Exactly. And because those vectors are updating every fraction of a second with new GPS and telemetry data, the closest point of approach is constantly being recalculated.
That is a lot of math happening very fast.
It is. The mathematical objective is super strict. That orthogonal distance can never fall below a heavily regulated safety threshold.
What kind of threshold are we talking about?
In aviation, that threshold is usually measured in nautical miles of horizontal separation and thousands of feet of vertical separation.
And if that calculated shadow shrinks too much, like if the math predicts that the toothpick is going to be shorter than the legal threshold?
The system doesn't wait for a visual confirmation. It immediately triggers a TCS alert, a traffic collision avoidance system warning.
Oh, wow.
It overrides the silence in the cockpit, alarms sound, and the software directly instructs one pilot to pull up and the other to descend.
So it forces them to physically change their direction vectors.
Yes, the math is quite literally an invisible buffer preventing disaster.
That's incredible.
And this identical logic applies to orbital mechanics too.
Wait, really? Like in space?
Yeah. Satellites orbiting the Earth at tens of thousands of miles per hour rely on these exact same cross products to avoid catastrophic collisions with space debris.
It's staggering to think that every time you fly, or every time a satellite beams GPS down to your car, the safety of that entire system is being guaranteed by vector projection.
It's just geometry doing its job.
It scales up to the massive expanse of the atmosphere and lower Earth orbit perfectly. But what happens when we scale in the exact opposite direction?
You mean downwards?
Yeah. What happens when the objects are completely stationary and microscopic? The notes talk about printed circuit boards.
Right, because the underlying math does not care about physical scale.
It's universal.
Completely. The domain of electronics and hardware engineering relies heavily on skew line theory, particularly in multi-layer printed circuit boards, or PCBs.
Okay, let me stop you there and play proxy for the listener's curiosity, because that feels really counterintuitive.
How so?
Well, if we are talking about a multi-layer board inside a smartphone, the copper traces, the microscopic wires carrying the data, they are separated by actual physical material.
Yes, layers of fiberglass.
Right. You have a trace on layer 1 and a trace on layer 2. They never physically touch. They are baked into different levels of the board.
That's true.
So why do we even care about the mathematical distance between them if there's already a physical wall separating them?
What's fascinating here is that the laws of electromagnetism don't respect physical boundaries the way we instinctively think they do.
They don't.
No. When a high-frequency electrical signal travels down a copper trace on layer 1, it isn't just moving cleanly through the wire.
What is it doing?
It generates an invisible electromagnetic field that balloons outward into the physical space around it.
Oh, kind of like a magnetic aura expanding off the wire?
Precisely. And if the shortest orthogonal distance between the layer 1 trace and the crossing layer 2 trace isn't mathematically vast enough, that expanding magnetic bubble from layer 1 will physically intersect the copper on layer 2.
Which means the magnetic field just junks the physical gap.
It does. It causes a phenomenon called capacitive crosstalk.
Capacitive crosstalk.
Yes. The magnetic field from the first trace literally pushes electrons around in the second trace, inducing a phantom electrical current that shouldn't be there.
Wait, so it's creating electricity in a wire that's completely disconnected.
Exactly.
Uh-huh.
Imagine you were transmitting a clean string of binary data ones and zeros across layer 2.
Okay.
Suddenly, that phantom current spikes, and it flips a 0 to a 1.
Oh, wow.
The data is corrupted, your phone drops a call, your computer blue screens, or your Wi-Fi router freezes.
All because the geometric distance between two microscopic skew lines allowed their magnetic fields to overlap.
Yes. So the physical gap between them, the actual thickness of that classic green fiberglass stuff in the circuit board, the FR4 dielectric material has to be perfectly calculated to prevent those auras from touching.
That is so wild.
And it gets significantly worse than just data corruption.
Worse how?
If the voltage running through those traces is high enough and the orthogonal distance is too small, we aren't just dealing with magnetic interference, we are dealing with high voltage arcing.
Like actual sparks?
Yes. The electricity can build up enough potential to literally ionize the fiberglass material separating the layers. A spark will jump the gap and burn a microscopic hole right through the board, permanently destroying the device.
So hardware engineers are essentially playing the exact same collision avoidance game as the air traffic controllers.
The exact same game, just measured in fractions of a millimeter instead of miles.
Okay, so we have seen this calculation protect commercial jets moving through the sky, and we have seen it stop microscopic circuit boards from melting down.
It covers a lot of ground.
It really does. But here's where it gets really interesting. What happens when the objects we're measuring don't actually possess any physical atoms at all?
Yeah. The notes take a sharp turn into virtual engineering, specifically software, computing, and 3D graphics.
So I get planes and copper wires, but how on earth does vector calculus apply to a video game or an animated movie?
It's all math.
But there is no physical distance to measure. There are no actual atoms colliding.
True. But to render a photorealistic 3D environment, the graphics engine needs to figure out what color every single pixel on your monitor should be.
Right.
To accomplish that, it uses a technique called ray tracing.
Okay, I've heard of that.
Imagine you're standing in a pitch-black room. You take a perfectly straight fishing line and cast it out into the dark.
Okay, I'm casting the line.
That fishing line represents an invisible ray of light shooting out from a virtual camera into the digital space.
And the engine needs to know what that fishing line hits.
Exactly. That ray of light is line 1. Line 2 is the edge of a polygon mesh. You know, the digital wireframe that makes up a virtual chair or a building or a character in the game.
Oh, I see.
Both exist entirely as vectors in simulated 3D space.
So the graphics engine is frantically playing air traffic controller, but instead of tracking planes, it is tracking millions of light rays and polygon edges.
Millions of times per frame. The engine constantly calculates the shortest orthogonal distance between the ray of light and the polygon edge.
Constantly checking for collisions.
Right. If the resulting distance equals exactly 0, it means the ray hit the object dead on.
Okay.
The engine registers an intersection and draws a solid pixel on your screen representing that object.
But what if it doesn't hit? Like, what if the ray just barely grazes the edge of the virtual chair? Does the engine just render empty space?
That is where the math transcends pure logic and becomes visual art.
How so?
If it's a near miss, meaning the calculated orthogonal distance is a microscopic fraction greater than 0, the engine doesn't just discard the calculation.
It doesn't.
No. It leverages that tiny fractional distance to calculate anti-aliasing weights.
Let's translate that for a second. Anti-aliasing is the rendering technique used to get rid of those jagged staircase-looking edges in graphics, right? It smooths things out.
It is. By knowing exactly how close the ray came to the polygon without actually hitting it, the engine can intelligently blend the color of the object with the background color.
Oh, wow.
It creates a seamless gradient. That invisible vector calculation is what creates incredibly realistic, soft shadows in modern media.
That is amazing.
The darkness of a virtual shadow perfectly fades into the light because the engine is measuring the exact length of that mathematical toothpick millions of times a second.
So the exact same cross product that tells a pilot to alter course is telling a graphics card how blurry a shadow should be.
It's the same universal truth. just wearing completely different clothes.
Unbelievable. But for a listener who loves to learn and immediately apply that knowledge, theoretical understanding is only half the battle.
Naturally.
How do we actually pull this out of the abstract textbook and run the numbers ourselves?
The source material provides two intensely practical tools for exactly this purpose. First, they highlight the absolute necessity of using an interactive spatial visualizer.
Which feels crucial, because trying to hold three-dimensional vector projections in your working memory while listening to a conversation is a recipe for a headache.
It really is.
You need to see it to really grasp it.
Yeah, the human brain isn't built to intuitively process raw matrix algebra. A spatial visualizer allows you to plug in those starting anchor vectors and direction vectors, and then dynamically rotate the digital space.
So you can actually manipulate it.
Yes, you can grab a line with your mouse, shift its trajectory, and watch that perpendicular normal vector recalculate and physically shift its orientation in real time.
It completely removed the abstraction from the equation.
It grounds it in something you can see.
And once you can clearly see the geometry behaving, you can code it. That brings us to the final piece of the source material, the 10-minute Python verification engine.
Right.
Which sounds incredibly technical, but what is the script actually doing?
It is a standalone Python script designed to directly implement everything we've just talked about.
Okay.
It imports standard math libraries, allowing you to feed in the raw data for your A and B vectors. First, it runs the exact dot products and cross products to output the analytical shortest distance.
But it doesn't just spit out a single number and call it a day, right? It goes deeper.
It goes a massive step further. The script dynamically sets up a linear system of equations.
Okay, doing the heavy lifting.
Exactly. It uses matrix algebra to solve for the absolute exact 3D coordinates, the specific x, y, and z points in space, where that orthogonal segment physically connects to both line 1 and line 2.
It finds the exact microscopic coordinates of both tips of the toothpick.
Yes. And finally, it plots the entire result in a 3D graph.
Wow.
You feed it the raw variables, and it programmatically builds the geometry, proving the theory right before your eyes.
Think about the power of what that script is actually doing. In 10 minutes of typing on your laptop, you are building the exact same mathematical engine that aerospace engineers use to route jets.
Pretty much.
You're proving the physical limits of reality right on your screen. So let's take a breath and look at the territory we just covered.
We covered a lot.
We really did. We started in a totally abstract space, hunting for imaginary toothpicks, using cross products and vector projections. But then we watched those concepts scale up to the sky, dictating the strict collision avoidance thresholds of air traffic control.
In orbital mechanics.
Right. Then we watched them shrink down to the physical FR4 dielectric material sandwiched inside a printed circuit board, preventing devastating electrical arcing and data corruption.
Which saves our electronics every day.
Exactly. And finally, we jumped entirely out of the physical world, exploring how virtual light rays use these exact same distance calculations to render breathtakingly realistic shadows.
It really demonstrates that math isn't just a descriptive tool we invented. It is the invisible scaffolding of the universe.
I couldn't agree more.
We've seen how a single absolute mathematical truth blindly dictates the physical limits of aerospace, the electrical limits of our hardware, and the visual limits of our virtual worlds.
It's kind of crazy to think about.
It is. And if this exact same linear equation perfectly maps onto so many wildly different physical and virtual realities, it begs an incredible question.
What's that?
As you look around your room or walk down the street today, what other invisible geometric forces and vector calculations are quietly governing the everyday objects around you right now, just waiting for you to find the equation?
That is something to think about. Next time you see a plane overhead or, just turn on your phone, remember the invisible geometry holding it all together. Thanks for joining us on this deep dive. Keep questioning the world around you, and we'll see you next time.